benefited so much from this conference over the years, so I'm very happy to make an attempt to contribute to the conversation and help others understand data centers, which is a topic I've actually been studying for quite some time, and maybe we'll share some of that with you. So our goal today is to explain the AI supply chain, which is sort of a high-level idea. You encounter it in daily life when you read a news article about supply chain problems in the chip industry, or about a not in my backyard problem in some state, or the revenue that OpenAI had last year. And the goal today is, in some sense, to connect all those things and make you help you understand how the data center sits between all those specific events. Now, there's two ways to do policy analysis like this. One is what I would call skate where you think the puck's going to be, and anticipate where you think it's what you need to know several years from now. The other way to do policy analysis is to look at the past and use that for lessons for today. And I'm going to do a synthesis of both, just to help you understand. So let's start off what's at stake, and why is it that we should use precedent to help us understand what's going on today. So we're in a situation, is really quite remarkable in U.S. economic history. Half of U.S. GDP growth last year could be attributable to the construction affiliated with data centers. That's the kind of concentrated investment boom we've only seen in a handful of moments in U.S. history. So a question you might reasonably ask is, how would you think about comparing the past to the present? And it's, we see it right now in things like a commitment being made by a county to let a data center go up. A utility has to make a decision today when they're deciding, should you dig up the street so you can get connectivity for this data center. And they're not thinking about this big picture when somebody has to float the bonds that then are going to be paid off over 20 years. But that's what's happening in real time as a result of this boom. And what's interesting about it, quite parallel with what we've seen in the past when we have investment booms like this, is you don't know what the payoff will look like for some time. We don't know at this moment whether the scale of demand, and I'll go into some details in a few minutes, but at the moment we have 1 billion users of OpenAI's product. That's kind of remarkable for a product that's just a little over 3 years old. The question is this, the growth rate that they've experienced over the last 3 years going to continue? Will we see that kind of demand in 5 years that would justify the kind of investments we're seeing now? We're also observing quite a bit of change inside business. And again, the open question is, will we continue to see that? And suppliers are, really the suppliers, as I'll talk about in some minute now, are up against capacity constraints. And the question is, will we see more capacity come into the market to meet demand, or are we going to be stuck with the kind of capacity we're observing? I often compare this to a gold rush, and that is actually a good comparison, which we'll talk about in a minute. So the historical analogy is we're seeing a large, big, lumpy investment, and the payoff is tomorrow. So how do we think about that? So what comparison might we use? If you are a student of history, you could compare this to what happened in the U.S. automobile industry just a couple of years after the Model T. This very parallel set of circumstances. You could also compare it to what happened in the television broadcasting industry just a couple of years after households started to widely adopt TV. I love the comparison with just a few years after the personal computer started to deploy into business. And of course, the comparison that I am most naturally suited for is just a few years after the commercial internet begins to grow, we could compare it to that. And let me push on the 1999 comparison because there are some useful lessons there. So why would you do this? Why would you compare the present moment to 1999? And I would argue there's many parallels. So to begin with, prior to 1995, there were many insiders who could talk about the internet and the web, and they were enthusiastic as could be. And if you talked to any of them, you had no idea what they were talking about, right? They could not express what was going on, and the only way to really understand it was to use it. Prior to 2022, and specifically November 2022, there were insiders who were talking about large language models with an enthusiasm. And for the life of me, I had no idea what they were saying. And if you talk to them, they were saying, look, this is going to change the future. But until ChatGPT showed up, until the Netscape browser showed up, the world just did not pay attention. Then a catalytic product shows up. Users understand from their own use. Investors understand from their own use. Suppliers understand from their own use. Oh, okay, now I get it. You can see what's likely to come. And so in response to that, you get growth of adoption rather rapidly. So by comparison, the Netscape browser by 1998 has 100 million users. By last month, as I said, OpenAI had 1 billion users, 10 times larger. And that's extraordinary, right? The extraordinarily rapid adoption of a product. I should say that scale changes things a bit, which we'll get into. Another parallel is that the core catalytic product starts as an application and then migrates into infrastructure. And we're seeing the same things start to happen now with AI. It started as application, but it is migrating into infrastructure for business. Other kind of fun parallel is that when Netscape showed up, Microsoft tried to buy them. When OpenAI showed up, Microsoft tried to invest in them. And there's a fun parallel there. Another fun parallel is that the World Wide Web Consortium was a non-for-profit and a very key organization, and OpenAI started as a non-for-profit, and then now we're not quite sure what they are. But there's a good parallel there. And then you can't make this stuff up. One wonderful parallel is life just goes on. In 1999, the pop star Victoria Posh Spice Adams married the footballer David Beckham. And, just last month, we had the pop star Taylor, not Ophelia, Swift, marrying Travis Kelce. Life goes on. Anyway, history rhymes is the point. And 1999 offers us some useful parallels. So how far can you go with that? Well, the parallel I really do want to push is that you see demand and supply evolving simultaneously and in sequence. The infrastructure has to go first, and then adaptation and integration come second. And that will be the theme that will play out today. And suppliers in this kind of situation are desperate for actionable knowledge, right? They want to know where value should go because they recognize that the revenue that this is going to generate is far into the future. And so any indication of getting that investment in the right direction is quite valuable. You don't want to push it too far. Number one, the scale of what we're looking at today is much larger than 1999, and that is going to have consequences. Number two, we'll talk about this in a little bit. The app space has evolved in very different ways than in the past, and the infrastructure space is also evolving in very different ways because of capacity constraints, and that's changing the structure of supply in some pretty important ways that we'll talk about. Finally, I have to we're also building on a different background, and so we have to explain some of that. So here's how I'm going to divide things up. I'll start with just giving you a walkthrough through the technical breakthroughs, talk a little bit about US geography, which is a big issue in this topic, and then we'll get into the user economics. So that's how we'll break it up. Okay, so I'm assuming everyone in the room sort of knows a little bit about this or seen a little bit about what the technical breakthroughs are. But I want to walk you through the core question that somebody 20 years from now, or a historian would ask, which is, why did this happen now? Why didn't it happen earlier? Why didn't it happen later? Why now? And the answer, if you go back to the technical advances that led to data centers, starts in 2005 in a very unlikely place, and that's with Mechanical Turk. So if you know Mechanical Turk, it's the microservices. You know, you pay somebody to do something for 10 cents, and they spend a minute on it, and then they move to the next thing for 10 cents, and so on. That's Mechanical Turk. Well, Mechanical Turk is opened by Amazon in 2005. You know, it was kind of a shot in the dark for the firm. They're kind of hoping somebody will show up. They are commercializing something they themselves are doing internally. Quite frankly, it is not a successful business for years. A few people show up, they get a few customers. Most people go, what am I supposed to do with this? And in 2009, Fei Li, who's a researcher, is suggested to her by a graduate student, why don't we use Mechanical Turk for the problem we face? And the problem she faced is she was trying to tag 1 million digital images. So, you know, dog, cat, tree, so that computer algorithms could read them and associate text with the images. And Fei Li gets a grant from the National Science Foundation, and she becomes Amazon Turk's biggest customer. and by 2010, has 1.25 million images tagged. And she could not figure out any other way to do it efficiently. Okay, so that's number one. Number two, once she has 1 million of these, she starts a contest in 2010. And here we get, yet again, big investment, you put it up online, and then you wait and you hope somebody shows up. And she starts this contest, and the plain fact is nothing much happens for a couple of years. Okay, so if you want to explain partially why we get where we are today, nothing basically happens until 2012. And it's investments that start 8 years earlier. Okay, there's one other investment. You've probably heard about this one too. The CEO at a gaming firm who's making GPUs for games. Just again, I can't emphasize this enough. NVIDIA is in the gaming industry, and they are one of the few survivors. And they make these cards that make your PC run better, and that's by doing parallel processing. And the CEO starts investing in scientific computing, a very different market for his chip. He does it as a consequence of hiring the first person as their dissertation to write an operating system for a GPU in 2004. So again, the technical basis for what we observe today goes 20 years back. And to all the credit of Jensen Huang for starting this, and they put out their first operating system from NVIDIA in 2006, and in 2007 they do an SDK, and you know, guess what happens? Nobody shows up. Right? And this is what happens for 5 years. There's a few experiments, you know, a few academic people show up and go, oh, this is interesting. What do you do with this? The key thing is Jeff Hinton recognizes a possibility, and he and two of his graduate students, brilliant graduate students, I can never say their names, Ilya Sutskever and Alex Krasinski, they put together an algorithm on top of a GPU-based card coming from NVIDIA, and it is way faster than anything else out there. And they use that in the they use that to develop a neural net for the ImageNet contest that Fei Li has put out there. And they put out their algorithm in 2012. Okay, so the most unlikely of things come together, and they win the 2012 contest. And Hinton will go on to win the Nobel Prize for this because it opens up a technical trajectory of new kinds of algorithms that nobody before had ever been able to do. Okay, so 2012, again, a dozen years ago. Then a bunch of things happened. I just don't have time for it. So I'm going to just sort of say, I'm going to skip, cut to the chase here. Scott and Nathaniel and I and two case writers at HBS have written this up. So if you would like to know the details, I'm happy to give you that. I'm just going to skip to the chase since we're about data centers. A couple of the pioneers who were in this community who are now trying all these new technical things run up against the bottleneck. And the bottleneck is the data center. The bigger the data center, the more they can do. It's that simple. And among those who run into this, it's Denis Hassabis of Google DeepMind, who is trying to first win games, AlphaGo, you might recall, and then solve a chemistry problem, which becomes AlphaFold. And particularly, he ends up using the Google invention of the attention mechanism, which is written in 2017, and a year later, they come up with AlphaFold, which is this simulated way of looking at proteins. And the number one thing he learns is that the better the computing, the better the AlphaFold gets. And they redo this, by the way, a couple of years later, and it is much better, just because they have better computing to work with. Another example that shows up around the same time is this odd organization, OpenAI, has its chief technology officer is Sitzgeber, again, one of the three who won in 2012. And he reads about the attention mechanism, puts it to work in a large language model, and within 2 years, the people at OpenAI recognize they cannot make progress unless they have a bigger data center. Again, they are right up against the bottleneck. And so what they do is they cut a deal with Microsoft to get access to their data centers in exchange for giving Microsoft an early look at what they were doing. And both parties benefit. OpenAI is able to do the first early versions of what you now have experienced as ChatGPT. And Microsoft, in return, by the way, from that early access, develops the first ever GitHub Copilot. Okay, and so both parties benefit from that. And the point behind both of these examples is the data center sits at the middle of these two acquisitions. Right? DeepMind is willing to sell itself to Google so it can get to the data centers, and OpenAI is willing to cut a deal with Microsoft so they can get access to their data centers. So just to alert you, it's already, if you were paying attention even in this era, you started to see, data centers are going to be at the center of things for a while. Okay, again, now a bunch of details. I don't have time. Again, just to cut to the chase. Again, you can read about it. And I'll just cut straight to the chase today. If you look at the data center today, if the capacity of a data center is the primary limitation on what you can accomplish, where are we today? It's a 150 megawatt data center today. It is the capacity probably last year that was determining most things. It won't be going forward. I think next year 300 megawatt is kind of where the frontier is, and it's moving, I should say, to about 1 gig pretty quick. That's where we are, and just again, give you a sense of why aren't startups doing this? Because it costs an enormous amount of money. So 150, again, just to give you a sense of the neighborhood, 150 megawatt data center, just to put the shell out, so just to put the building, that's a $2 to $4 billion expense. I was interviewing somebody not too long ago about making one of these. And they remarked that it took 20 acres of land, okay, and then a staging area of about 80 acres. So just to give you a sense of what it took. Then that's just the shell. Then you have to fill it up with the hardware. Okay, so depending on how close to the frontier you want to be, last year, if you wanted to be at the frontier, $15 billion. But for some purposes, you don't have to be. You could be $5 billion. Okay, that's the scale, again, of what the hardware costs. Operating expense, about $500 million a year, depending on where you put it. It's a little less if it's in a cool environment, a little more if it's in a hot environment. And then you have to replace the hardware at some regular cycle. So that's an operating expense from the viewpoint of the data center. And again, that's $1 to $5 billion, depending on what you want to accomplish. Okay, just to give you a sense of the scale. And that's why you don't find anything other than a few large players here. It's just the financing of this is quite substantial. Okay, so we are today looking at 1 gig as the goal, and Meta has on its books plans to put a 5 gig data center in Louisiana. That's what people are talking about. And you might reasonably ask, why? And from a technical standpoint, the answer is they have not encountered what an economist would call diminishing marginal returns. They have not yet. Again, from a scientific standpoint, it's a very unusual situation. The attention mechanism in transformers has not yet run out of steam, is another way to say it. They have found they can put 2 billion tokens in their algorithms, and it still gets better. So the computer science community believes they can add several billion, and it'll still get better. They have just not run out of room. And the big firms are betting that that's going to continue. And if you talk to them, they, at the moment, do not know where this will end. Okay? Scientists, if you talk to the best scientists in the world, they don't yet know where transformers will reach its natural limitation. That's why they're building. They think they can continue to make progress. And sometimes when I have these conversations with someone who hasn't been paying much attention, the natural reaction is, whoa, wait a minute. Isn't that going to lead to the singularity and end the world? Okay, so you might have had that reaction too. I treat that as science fiction. So if you would like to do that, that's fine too. I'm okay with that. But I recognize this is part of the conversation. On the other hand, the cybersecurity threats that this raises are actually quite down to earth and quite real, and they scare the crap out of me. So I'm going to share that with you in a little bit, but that is a real threat, a real thing, which we'll get to. So that's kind of where we're going. Just to say, I've just talked about NVIDIA. That is just to fill in a little bit of, again, we don't have a ton of time to talk about this, but there are other approaches. Google was one of the early developers of an alternative, it's called a tensor processing unit, an alternative way of doing the chips. AMD has a model that's pretty competitive. There are several others putting them out. And you can put together data centers based on them. The principal limitation on all of these right now is capacity to produce them. The supply chain for chips is design and then manufacturing. TSMC is the largest manufacturer in the world, and they have limited capacity for the requests they are getting. That's principally it. And for example, the capacity they're putting in Phoenix right now will help a great deal on this. But that's where the major limitation is coming from. There's another limitation. We could get into the details if you're curious. When you put together a data center, it's not just computing chips. You also need a lot of memory for virtual memory, and that is drawing a lot of the memory market demand right now. And you will notice this because your iPhone is more expensive, because all memory chips everywhere are being competed up in price. And so that's again, a serious constraint happening worldwide. So again, just want to emphasize, right now, this won't last, but right now, the primary constraint we're all observing, and the thing driving prices and costs up right now are manufacturing capacity, not design. Okay, one other last natural question, and then we'll move to geography. Again, whenever I present this, people ask, well, wait a minute, didn't the Chinese firms all do this? And they don't have data centers like this, and that is correct. They don't. And so how do they manage to do that? Well, what they're doing is distillation. And it's, what that amounts to is about tens of thousands of prompts to an existing model to extract what its underlying logic is. It's a very natural thing if you're second, by the way, to have an open model. That's from a strategic standpoint, that's the right thing to do. Then, the question that almost always follows, so I'll anticipate is, isn't that cheating? And the answer is, well, yes and no. The no part is, if you were second, you would do this too. And distillation existed before this, and so in some sense, it's nothing new. It's always cheaper to be second because you know what the goal is at that point. Somebody's figured it out. It is cheating in the sense that if you do read their news announcements, they are not being honest about the subsidies they're receiving. They are using chips that they're not allowed. The U.S. government has liked to prevent them from using. They are definitely using them, but they can't admit it. And so that's going on behind the scenes. Okay. Here's the other remark. They are at the moment doing open models. Also within the Western world, there's also quite a number of open models. Meta supports one in particular that's quite prominent, but there are a number of different open models. Usually my reaction, until this year, I would say, my reaction about open systems was that this is good for the world. Most of the time, it offers more competition. It's an easy way to find experimentation. The proprietary firms are watching what the open communities are doing and learning from them. However, if you were paying attention, and if you haven't read up on this, this is worth reading up on. It is a core event. The hub for open models on the planet is a place called Hugging Face. It has about 1 million models sitting on it. It gets another model about every minute that in the open source world. They were broken into just last month by one of the agents coming out of one of the labs. And the thing that we learned from watching what happened there is that these agents are capable of breaking into almost anything. Look, Hugging Face is among the most sophisticated hubs in the world. And they got broken into. For 2 days, they didn't know what was going on. They didn't know how to deal with it. And then after a week, they figured it out. And if that's the most sophisticated hub in the world, and that's their experience, imagine what's going to happen when your local hospital gets broken into, when your local school district, your local government. Okay, this is telling us, please, this is telling us, this is a very dangerous situation. And when a rogue actor gets access to the open models, I think we can expect to see this quite a bit. And this scares me a lot. Okay, so just to be clear. Okay, so let's go from nightmare into geography. So geography, how do you think about the geography of data centers? A data center, when it tries to locate, we have a long history here, you want to get some land, you want to get connectivity, you want to get the coding up, you get hire construction crew, you get the racks and servers, you get some permissions from the local community, that's how you build them. What has changed? Number one, concerns about water use have changed because of the scale of the new systems. This is a solvable problem. I can't emphasize this enough. You just don't do evaporation anymore. You have to do recycling. Okay? It costs a little bit more. It's pretty straightforward. The community doesn't want it. You just require it. That's it. Okay? Number two, concerns about electricity. I'm going to let the next panel talk about this. Okay? That's a serious concern. AI vibes. For better or worse, people are scared of AI. I don't know why. Hollywood's been doing this for 20 years. Is anybody surprised? The world's scared of this. And NIMBYism has definitely emerged. With it, again, not a surprise because the supply is being put in one location and the benefits going somewhere else. Right? The users are all elsewhere. So, Okay, so here's a way to visualize how things have changed recently. This is from a project that Tommy Pan-Feng, who's a professor at Rice University, and I did a number of years ago about what the data center market looked like prior to the pandemic. And when you locate what the data centers look like prior to the pandemic, that's an era where everything is about a 5 to 30 megawatt data center, and they are almost all in urban areas. They're all co-located next to their customer. The sort of interesting exception in those days was AWS, who was putting up 20 to 30 megawatt data centers. And even they, when you look at the architecture, what they were doing, they would put their compute in these low density areas, but then they would locate a bunch of the compute right next to their customer because, again, their customer wanted to get fast service. And so you found that the concentration of where most of the capacity was in urban areas, and you could open one of these things, and you could put it in a suburb. It didn't have to be necessarily downtown. It can be a couple miles away. And so it just did not run into any issues inside most urban areas except to get the permissions, to get the connectivity and the electricity. When you look and you ask, again, in that era, what was the constraint on capacity, many of you from the DC area, so here's a map of what things look like. On the x-axis is the log of the population of the cities where the data centers were going. On the y-axis is the square footage of the data centers. And it was a fairly straightforward relationship between the capacity of data centers and the size of the city in which it's located. That is a pretty straightforward economic relationship. The sole exception, the big exception I just point out here is Ashburn, Virginia, which many of you who live in DC area have experienced. It's got a capacity way out of scale with its population. And it's sort of a very interesting exception to the rule, but prior to the present era, that was the exceptional place. By the way, it is not going to be the largest location for capacity in the US in another 5 years, but it has been until now. The interesting thing is, even in that era, you could see the low density areas were starting to get capacity, and that were all the hyperscalers coming out of Amazon and Microsoft and Google at the time, and Meta. If we were to make the same graph today, it would look very different. Just to give you an example of what was happening in that era, this is Prineville, Oregon. It's a population 10,000 people. This is where Meta was putting most of its data centers in this time period. They would build them 30 megawatt data centers at a time. So they would build them sequentially. They started this in 2010, and they have something like 180 megawatts in Prineville now, okay? And that's running your Facebook and your Instagram, actually. This is what's doing the big compute on the social network that you bring up on your phone. Okay, then why can you do that so instantaneously? Because this thing is computing all the time. It's re-optimizing every hour. Okay, so that's as big as things got, okay? And now Meta is planning a 200 megawatt data center in Altoona. They've got a couple 1 gig things planned, and they've got this one on the books for 5 gig in Louisiana. Okay, so that just to tell you the scale. This is what used to happen, and now we're moving to this new era. And then if you look at where this new era is, here's this nice convenient map that the New York Times published only last month. And when, by then Scott had given me this assignment. And I was like, oh man, I got to get a map of what's happening. And the Times was nice enough to do this. You can just see most of the growth is ending up in low density areas. And that's because it's no longer following customer, it's following energy, right? It's following input. And a high fraction of it is following natural gas, actually, so that you can put a gas turbine next to natural gas and run off grid. And so availability of electricity is becoming the primary determinant of location. And again, next session, I can punt and let the next session do that, talk about that. So again, summarizing, if you're looking at the geography, what's happening now, Most things are going into low-density areas. Construction now has turned out to be the primary bottleneck. There are only so many construction crews in North Dakota, okay? There's tons of natural gas, but it's just only so many electricians who know how to put together a data center. Again, I'm interviewing somebody at the moment for a case about this, and it's just fascinating. That's the constraint they face. You have only so many crews. West Texas, which is where a lot of this is also happening, everybody is employed. Again, I was interviewing a firm, and they said, we're not bothering to go to West Texas anymore. We can't get any more people. Everybody's bid up. Everyone's got contracts for the next 3 years. Why would we bother? We'll go somewhere else. And that's a big constraint. There's shortages of generators, particularly natural gas generators. That's a big constraint. And fabrication of GPUs, as I mentioned earlier. So those are the primary things that are determining supply right now. Let me just develop one implication, because I hinted at this earlier. So what's happening in the supply chains to build data centers is that if you're a supplier and Meta or Google, perfect. If Meta or Google wants something from you, what are you going to do? You're going to supply somebody you've done business with your whole life. And then the new entrants are going to get treated less as a priority. And the consequence of that, because it's happening at every supplier, the consequence of that is that the new entrants here are having a much tougher time getting the parts they need to have a sufficient supply. And whether we like it or not, it has led to a structure of supply that is favoring the existing players. And so if I'm giving a very simple explanation for why are we observing less independent supply than you might have thought, it's coming from the supply of parts. That's the explanation. And it's a very big difference with the dot-com boom. Right? The dot-com boom had a huge independent supply response to the demand for application. And we could have had that here had we had the supply of parts, but we're just not getting it. Okay, so that is a big deal. Okay, and we will live with that consequence for a couple decades. All right, finally, I'm going to end with 5 minutes ago. What have we seen so far on the user side? On the user side, 1 billion users and quite a bit of adoption in business. It's pretty widespread. Plans are pretty widespread across industries. It's very interesting. It's not concentrated in the usual early demanders for frontier digital services. Typically, that's finance and our big players like electronic commerce and insurance and a few other areas. Those are usually, and logistics are usually the industries that are first movers. This is much more widespread. So that's a pretty interesting feature. We have a bunch of surveys to show that. And the scale of the dollars that are going into this in business is pretty substantial and is going to exceed what we are observing at home. The total addressable market's quite large, potentially quite large. And the big open question is when we're going to see many of the dollars go into investments. That's the big question right now. And if you're a supplier, it's a lot of uncertainty about when you realize revenue. And so if you watch the stock market or investor analysts go up and down about who's profitable and who's not, that's what's driving it. They don't know when they're going to realize revenue completely, what the timing looks like. And that's because we don't know. Partly it's because we're experimenting still, and so we don't know where the big payoffs are. And this is very parallel to what happened in 1999. When businesses were putting investments into the internet, really that boom continued all the way until about 2003, and then there was steady investment in electronic commerce from then on out. And so by parallel, if you were trying to ask what do we expect to see in a parallel sense today, you expect to see a lot of deep but narrow investment in very particular functions inside of businesses as they experiment to try to get a payoff. Most businesses aren't going to make an adoption of AI with a payoff 12 years from now. They'll look for something that they were structured to try to get a return on their investment in a 3 to 5 year time horizon. And the plain fact is they're not sure. So we are observing a lot of experiments right now. That's very parallel to what happened in 1999. Core difference today is the scale of it is much larger. Another thing, it's very hard to measure, and yeah, that's basically it. And in the interest of time, let me keep going. So the other thing I would say if the past is prologue, what would you expect today? If you go back and you look at the investments that were made in electronic commerce in particular, and when there was the biggest payoff, the fascinating thing, go look at your phone today and what apps you use. Virtually all of them were invented after 1999. I'm looking over at Jeff Prince. We've done a lot of work on where users put their time. Just look at the top 100. Virtually all of those are businesses that did not exist in 1999. They came into existence later. And so, I can just put a list up here of things that came a decade after the initial commercialization of the internet. And so if I were forecasting for commercialization of AI and large language models in particular, what to expect, the forecast is we ain't seen nothing yet. We're going to be seeing, we're in the bottleneck phase now, and then we should anticipate applications showing up after these bottlenecks get resolved. Okay, so let me finish up by saying that is why when you look out today, you see huge investments, but you don't see revenues of consummate scale. That's exactly the moment we are in. The biggest investment revenues you see today are OpenAI is $6 to $7 billion last quarter. Anthropic's about 10 to 11 billion last quarter. The big firms don't separately tell you what their revenues are, but nobody thinks it's of that scale. And Scott wants to keep me on time, so I'm just going to keep going and finish. Yeah, and so here we are. The capital is lumpy, capacity is large, the commitment's indivisible, and the pace is that we have a lot of supply and a lot of demand is about to follow, and we don't know what that demand's going to look like. And there we go. Yeah. Thanks. Okay.
There were a number of them, but one of them was in fact the overinvestment in networks that took place, overvaluation of wireless, all these things that would eventually pay off, but it had this pie in the die kind of. Do you think that we're looking at something similar here, or is there something about this kind of supply chain that makes it different?
Yeah, I mean, you can make one, if I knew exactly, I wouldn't tell you, because then I could invest. The frank answer is it's inevitable that demand and supply won't align. I mean, that's the right way to say it. It's inevitable because exactly what we just said here. It's a lumpy first investment, and then demand has to show up eventually. If we're fortunate, demand shows up sooner than later, and then you don't get what we got in the dot-com boom. I mean, the dot-com boom and the bust was also facilitated a bit through, financial shenanigans. Yeah, and we have less of that here. We have some. We have like the circular finance. So that's the parallel. Yeah, that's a good question, right?
I think we got it.
Okay, cool.
But Shane will be around.
I'll be around, yep.